You can go.
All right, hi everyone. Welcome once again to the set theory seminar. Today we have Richard Matthews from the University of Leeds speaking again. Glad to have him back. And he will talk today about big classes and the respected model. Go ahead, Richard.
Right, thank you very much. So thank you for inviting me to come back. It's always nice to talk here virtually, whatever it is. So today I'm going to be talking about big classes and the respective model. So this is something that I started working on during my thesis, and I've sort of starting to come back to it, and this was a good opportunity to think about it properly. So to begin with, I'm just going to introduce the main theory that we work in, which is ZFC without powerset. So under ZF without replacement, so Zermelo's set theory, we have three versions of the replacement axiom, which are all equivalent. The first is the reflection principle, and this is stronger than the collection scheme, which is again stronger than the replacement scheme. You can easily see the first one implies the second one, which implies the third one, and over Zermelo's set theory, all three of these are equivalent. However, without powerset, the reverse implications break down. The fact that replacement doesn't imply collection is quite an old result by Symmetric, while collection does not imply reflection is a relatively recent result by Friedman, Gitman, and Canove. So therefore, we're going to separate the three theories and look at the different properties of these theories. So to begin with, we let ZF with this central minus be set theory without the powerset axiom and only the replacement scheme. We're then going to use an upper minus, upper meaning it basically is a stronger theory, to be ZF with the central minus and with the collection scheme. Then again, all of our choice principles are no longer equivalent without powerset. So as our choice principle, we'll take the strongest natural one, which is the well-ordering principle, and that'll be ZFC minus. And equally for ZFC with the central minus, we'll again take the well-ordering principle. And finally, just because I can't make my minus sign any higher, I'm going to do ZFC minus sub ref to be with the reflection principle. And these theories are talked about, particularly in this paper, what is the theory ZFC without powerset by Gutman, Hankins, and Johnston. So now for mu of regular cardinal, H mu is a model of ZFC minus with reflection and lots of other nice properties. So it's sort of the standard one that actually helps. However, if we only take replacement as our collection scheme sort of thing here, then these models can behave very counterintuitively. So just to give you some examples, which all appear in the paper, what is the theory ZFC without powerset? So without collection, we can have models where omega-1 exists and is singular, where exists and every set of reals is countable, where for every n, there's a set of reals of size aleph n, but none of size aleph omega. The Wash-Ultra power theorem may fail. For the ones that, so these are sort of standard ones. For ones more interesting to me, Geifman's theorem can fail. So we can have a cofinal sigma-1 elementary embedding, which is not fully elementary. Or we can have things like the class of sigma-1 formulas not being closed under boundary quantification. So phi can be a sigma-1 formula, but the statement for all x in a phi is not sigma. All of these problems go away if we assume collection. So this is sort of the conclusion of this paper, was that ZFC minus with collection is the correct way to state ZFC without powerset. And we're going to sort of see, as we look through a lot of examples of things, that these are also the natural models. If you just do standard procedures, for example, class forcing, which we'll look at later, the class forcing preserves collection if you had collection in the ground model. So this is why these are the obvious correct ways. And what I sort of want to go for today is to tell you why this is actually not always the case. Why there are some very natural models where you would expect collection to hold if you just think about it naively, but actually collection fails. I should say now, if you have any questions, please ask and interrupt me any time during this talk. So this is our main theory that we want to work with, sort of models of ZFC without powerset for various formulations. And the first thing I want to talk about are big classes, which is one of the main things in my title. So this was me trying to, I was trying to think of an idea that essentially summarizes what a proper class is in set theory and how we actually use it. And the general theory in ZFC is you're a proper class if you are too big to be a set. And what do I mean by this? Well, in a formal way, we can say a proper class is big if it surjects onto every non-zero ordinal. And sort of this is just for me. So this is why I care about big proper classes. So if you take some weak theory, I've said ZFC without powerset and only replacement, even weaker than that's fine. And you take some elementary embedding from B to M. And now if C is a proper class and J is the identity on C, then you can prove C does not surject onto the critical point of J. And therefore this means that, for example, the power set of omega cannot be a big proper class, if it is a proper class at all. Because if the power set of omega was a big proper class, it would have to surject onto kappa in this situation. So therefore, if we were to exist in a universe of ZFC without power set and every proper class is big, then the existence of an elementary embedding from B to M would imply the power set of omega is a set. And this has some nice and interesting properties, which I'm not talking about today. And then, so the question is, when does this hold, this notion that every proper class is big, and when does it not hold? And to give you the first example, to give a nice simple example, well, over ZF, every proper class is big. So it's nice, easy.
Sorry,
Yep.
Richard, can I ask a question about your definition?
Yes.
So you say that the intuition big is it's too big to be a set. Naively,
Yep.
I would say it's about existence of injections, not about surjections in the other direction. Are these equivalent in your context?
These turn out not to be equivalent. Do I have the proof of this? I do have. I will mention that proof in a minute, in a while, because I can't remember which slide it's on. But no, so you can have in ZF, you can have a proper class which is Dedekind finite. So you can have a proper class and omega will not inject into it.
Okay, awesome. Thank you.
So yes, this was by Monroe, and I will bring the formal statement up when I get to it. But yes, so it turns out injections are completely the wrong definition, but that was a very good question. Yeah, injection completely wrong definition, surjections turn out to be a much nicer way of doing it. So yes, as I was saying, over ZF, every proper class is big. So to see this, well, let's just take a proper class C. And now we're going to just look at the rank of the elements of it. So you can easily see that the rank of the elements of C must be unbounded in the ordinals. Otherwise, C would be a subset of sum V alpha, and then we can use separation, assuming our C is definable, because otherwise, what are you doing? So therefore, S is unbounded in the ordinals. So given an ordinal alpha, we can take the first alpha many elements of S, and this gives us our surjection. So ZF, the answer is easy. So let's look at some weak theories. So the simplest weak theory being Kripke-Platek. And in this case, KP gives us we can have a proper class which is not big. For example, the L aleph omega of L. So you can easily see by, since the fact that every cardinal is admissible, that L aleph omega of L is a model of KP. Now, in our external universe, we know there are only omega many cardinals in this model. So therefore, card does not surject onto aleph 1 of L in L. So therefore, there can be none in aleph omega of L of aleph omega of L. So this sort of tells us that if we don't have enough separation, then we're going to have proper classes which are big, which makes sense because without separation, we have subsets which are proper, which become proper classes. The second example, this is a long and tedious statement of the theorem, but the second example is a model of ZFC without power set and with only replacement, in which there are proper classes which aren't big. So the idea is we're going to take a model of ZFC. We're then going to instead we're going to add Aleph kappa many reals, but we're not going to add them all in one go. We're going to start by adding the first gamma many for each gamma below Aleph kappa, and then we're going to slowly add these chunks more and more. And it turns out that if you do it in this way, you can prove powerset obviously fails, and you can prove that collection also fails. However, because V and VG have the same cardinals, W must have the same cardinals as V and VG. And in VG, the powerset of omega is Aleph kappa. So there is no surjection of the powerset of omega onto Aleph kappa plus 1. Hence, there is no surjection in W. But powerset of omega in, say, W, you can prove is a proper class in this model. So W is a model of ZFC without powerset and any replacement with a proper class that is not big. And the interesting thing to note here is that we have the DC alpha scheme for every alpha below kappa, but not the DC kappa scheme. And this turns out to be important. So just to let you all know what the DC kappa scheme is, and I'm just going to give it very vaguely because I'm not going to talk too much about it here. For mu and infinite cardinal, we call the DC mu scheme the assertion that for any definable class tree of type mu, which has no maximal element and is closed under sequences of length mu, we can find a branch of order type mu. And so this is just the obvious generalization of the DC mu axiom to a scheme for classes. Right, so for mu equal Aleph 0, we'll call it the DC scheme. And just for those who aren't really aware of DC, I thought I might mention some basic consequences in something like ZF. So the bare category theorem is equivalent to DC. Downward Lowenheim's golem is equivalent to DC. It gives you that sort of choice for countable families. Every infinite set has a countable infinite subset. Aleph 1 is regular. It's a nice axiom to assume. And it turns out there's another nice characterization over ZFC without powerset, and this is that the DC scheme is equivalent to the reflection principle. And this is sort of what they then use to show that, what Freeman, Gibbon, and Canova use to show that the reflection principle is not provable in ZFC without powerset. But what it does have a use for is, well, if you take a model of ZF without powerset, and you take the DC mu scheme for mu and infinite cardinal, then if you give me any proper class, I can find a subset of it of cardinality mu. And I won't give you the proof here, but it's essentially that, well, we're just going to iteratively choose more and more elements of our proper class. This is a tree structure, basically. And as it's a proper class, we can't have a maximal element of our chain. So therefore, we can just use DC mu to create a branch through the whole thing. And therefore, what we get out of this, well, if you take a model of ZF minus plus DC mu for every cardinal mu, then every proper class is going to be big in our setting. And in particular, this is what I then sort of used in a paper that I talked about last time I gave a talk here, which is that if you take a model of ZF minus plus DC less than the critical point of J, but that's not important. So if you take DC mu for every cardinal mu, then you can prove that both the power set of omega and V crit J are sets, given an elementary embedding. Right, so just to sort of conclude the bit about big proper classes, is that we have this nice diagram. So above the top blue line, so ZF, ZFC, ZFC without power set plus for all mu, DC mu, every proper class is big. While below the line, so this is without a power set and with only replacement, we can have models where proper classes are not big. So the obvious question is, well, what happens if we have if we don't have power set, but we have collection? Is every proper class big in ZFC without power set, but with collection? Well, spoiler, the answer is no. So this is a joint work with Vika, which is interesting in completely different reasons, and therefore I won't be talking about today. The answer is we can find models of ZFC without power set, with collection, and with DC alpha for a bounded amount of, for boundedly many alpha, in which there's a proper class which is not big. That I said, I'm not going to talk about this. Instead, what I want to talk about is a failed attempt. So this was an attempt that I had a discussion with Johannes Schertz pre-pandemic, so a very long time ago, and in which I asked him about this question. And we came up with a model which we thought would work, but it turns out doesn't. So let's start with a model of ZFC. Let's consider the forcing to add odd many omega blocks of Cohen wheels. If we take a generic for this, you can prove MG models ZFC without power set. I will formalize all of this in the really long section you can see in the slides called formalization. So we have this, and now we're going to take our symmetric submodel in which these blocks of form an amorphous proper class. Again, it doesn't matter if you don't know how you produce this model. The fact is there is potentially a way that we can produce this model. And by the way, we call an infinite class amorphous if every subclass of it is either finite or cofinite. So we have this amorphous proper class, and now I want to claim that because ZFC without power set and with collection was the right way of thinking about things without power set, and because all natural models one produces satisfy collection, I claim N is a model of ZF without power set and with collection, in which there's an infinite class which doesn't surject onto omega. And just so you know why it doesn't surject onto omega, well, let's take our amorphous proper class A. Suppose A surjects onto omega, then I could look at those elements of A which are mapped onto odd numbers and those elements of A which are mapped onto even numbers. These are two infinite subclasses of A, which contradicts it being amorphous. Okay, so I claim that we're done. However, this doesn't work. So it turns out that if we take a model of ZF without power set with only replacement here, in this language with our predicate for A, and A is a proper class, such that if B is infinite, then B is a proper class, an infinite subclass of A. So in particular, when A is amorphous, then the collection scheme fails in our model. And in fact, our model doesn't have a cumulative hierarchy, so power set will always fail in these models. And this is actually exactly then the same if instead of an amorphous proper class, you try to add in a Dedekind finite proper class of reals using the Cohen's first model, for those who know what that is. And to just prove collection fails, it's relatively straightforward because for every n, we can find n many elements of A. But then if collection were to hold, we should be able to collect all of these into a set, but then this would form an infinite subset of A. But we know any infinite subset of A must be a proper class. So we've reached contradiction. Okay, so what went wrong? So we started with our model of ZF without power set. We know that class forcing is called pre-tame. Again, I'll talk about this more in a minute. If for any generic MG model ZF without power set, and we know adding odd many Cohen reals is pre-tame. But the collection scheme failed in N. So therefore what we've shown here is either something goes wrong in trying to do symmetric submodels for class forcings, which I will show nothing goes wrong, or the symmetric submodel of a pre-tame class forcing need not preserve the collection scheme. And in fact, I have absolutely no idea what the symmetric submodel actually satisfies. I can't even prove it satisfies unions. So it looks horrible. But just to sort of give you the counterside of that is sort of another reason why we care about class symmetric systems in general is these also produce really interesting models of ZF. So a typical example being Gittich's model, where every kernel is singular. You can show that the forcing is pre-tame and power set fails, but the symmetric submodel satisfies ZF. So sometimes our model will satisfy ZF, sometimes our model will satisfy ZF without power set, but with replacement. Sometimes it'll satisfy collection. Sometimes I have absolutely no idea. And this is then what I've been trying to study here, is to try and work out what this model actually satisfies. Right. Are there any questions at the moment? Good. Okay. So having sort of introduced the main concepts, I now want to sort of formalize everything, just to make sure that the symmetric submodel is actually definable. It could be the case that for some odd reason, when you try and do symmetric forcing, everything breaks down with classes. It turns out that won't be the case, but we need to check. So there are two sorts. There are sets. If we work in second order set theory, because we're doing class forcing, so we need to split into two sorts. Firstly, we have our sets, which are always denoted by lowercase letters. And secondly, we have our classes, which are denoted by uppercase letters. And our model of second order set theory is going to be some triple BEC, where V are the sets, C are the classes, which should be a script. It's a script C because it's a higher order element. Then every set is going to be a class, and classes consist of sets. So this is our basic premise we're going to work with. And then the main theories one works with things like Gödel-Bernays set theory. So this is where our set axioms are ZF. We use class replacement. So if F is a function and then F restricted to A is a set, at least set A. And we use first order comprehension, which means if you give me a first order formula, so this is a formula without class quantifiers, right, then the collection of x's such that phi x a holds is a class. And it turns out GB is a conservative extension of ZF. And if you take a model of ZF, then M with its definable subsets is a model of GB. So it's perfectly harmless to do this in general. So then just to give you some more of the theories, with GB with a little c is to add set choice, so every set is well orderable. GB with a big C is with global choice, so every class is well orderable. And then sometimes we want to go even stronger than this, so we take Kelly-Moore set theory, where we add second order comprehension, which says now I'm allowed to, in my comprehension terms, I'm allowed to quantify over arbitrary classes. And yeah, Kelly-Moore implies consistency of ZFC. It's a lot stronger than ZFC. And natural models occur with V kappa and its power set. Okay, so we've now got our main setting. So now I can talk about class forcing. So essentially class forcing is, instead of a set forcing, so P being set, P is now going to be a class. So we got our partial order, P such that P is the class. Again, we'll just say it's generic if it reaches every dense subclass of P. And in that case, we could define a forcing extension. So now for everything to behave nicely, P needs to satisfy the forcing theory, which consists of two lemmas. The first being truth. So if you're true in the generic extension, you're forced to be true by some element of the generic. And the second is definability, which says that the forcing relation is definable in the ground model. The issue is, in class forcing, the forcing theorem may fail, even for atomic formulas. So we have to be careful here. But it turns out, so by a paper by Holly, Look, Niemor, and Schlicht, that if we take a countable transitive model of GB, then there is a forcing which does not satisfy the forcing theorem for atomic formulas. So we know that it is important that we make sure that we actually satisfy the forcing theorem. We can't just take it for granted. But then they also prove in this paper that it suffices to just prove the forcing theorem for, or the definability lemma rather, for a single instance of U and V, or U equals V. And if you can satisfy it for those, then in fact you satisfy the forcing theorem for every formula. And now just to give you two sort of nice types of forcings, they have better definitions, but for the purposes of this talk, starting with a model of GB without power set, but with collection. So this should be second order collection in this formalization. We call our forcing pre-tame if whenever you give me a generic, we preserve GB minus. And then secondly, we're going to call a forcing tame if when I start with a model of GB, every generic satisfies GB. So just to give you a bit more details on this. So both pre-tameness and tameness, as I said, can be formally defined by satisfying a combinatorial property, but I don't care about that in this talk, so that's fine. Also, if you are pre-tame, you can prove you satisfy the forcing theorem, so I'm not cheating. And the second point is that if you're pre-tame, you're pre-tame if and only if you preserve GB without powerset and only replacement. So it suffices to prove replacement, and then we get collection for free. Again, emphasizing the fact that with collection is the correct way of doing models without powerset. So just to give you some examples. So of tame forcings, we can force GCH to fail or hold at every regular cardinal, make every supercompact cardinal label destructible, add a global well order. If you only want pre-tame, you don't care about powerset, add odd many Cohen wheels. And for an example of a forcing which is not pre-tame but still satisfies the forcing theorem is the one to add a surjection from omega onto board, where you can easily see, well, the range of this function is a class. So therefore, we've broken replacement. Okay, so this gives us class forcing. So now the next thing we want to do is symmetric class forcing. And for that, I have to briefly introduce the notion of a symmetric submodel for those who don't know it. So for this one, this will be the symmetric submodel to add a Dedekind finite set of wheels. So let's start with a model of ZFC and take P to be a forcing, for example, adding only the many Cohen wheels. We take G to be the group of order-preserving automorphisms of P, for example, the automorphisms generated by bijections of omega. And I've slightly lied here. K is actually, it's not the full power set of G, and this is just, I'm going to need this for the next section, but K is actually the collection of subgroups of G, but they're basically the same thing. So in these setups, then we're going to call F a normal filter of subgroups if, well, it's a subset of K, which contains G, so everything's not empty. It's closed under intersections, is closed under supersets, and it satisfies something called normality, which is that if pi is in G, H is in the filter, then pi H pi inverse is also in the filter. A typical example being the filter generated by fixing finite subsets of omega. So such a triple we're going to call a symmetric system. And now we can look at those names which are symmetric. So to make our symmetric submodel, we basically want to restrict our attention from all names to just a nicely behaved subclass of them. So we're going to call a name symmetric if those permutations which fix X are in the filter. And we're going to let HSF denote those ones which are hereditarily symmetric, by which I mean X is symmetric and every element of X is symmetric, but not necessarily by the same group in the filter. The symmetric submodel is then NG, which is X.G for X being a symmetric name. And we can prove that NG is a model of ZF, which sits between M and the full extension. And in general, it will not satisfy choice. And one of the most important properties in order to actually do anything with all these models is that it satisfies the symmetry lemma, which says that if P forces 5x, then pi P forces 5 pi of x. So this is what happens in the set case. We now want to look at the class case. And before I do that, I'm just going to go back and look at what actually happened in the set case. So if we wanted to generalize this to classes, well, we're going to start with our universe. So this is our set of first order objects. We're then going to take P being a class forcing, so that's a second order object. G is then our group of order preserving automorphisms of P, so that's a third order object. And now we want to look at the filter of normal subgroups, which is a fourth order object. Which means you need to go away and cry in a dark corner for a few minutes. And then you need to accept that in order to formalize all of this, we're going to formally need to work in a model of fourth order set theory. One sec. So I very much do not want to define fourth order set theory today. And also I do not believe, I've not found anywhere it appears in the literature. So if anyone's read anything about higher than second order set theories, anywhere in the literature, I would be very interested to know about it. I've written a definition down for what I want, but it's not very nice. But anyway, for the purposes of today, I'm going to take a model of...
You really can't get away with somehow using simple enough objects to lower this. This is awful.
I know, but the issue is if I want to
Very
express it in full generality, really you do need to go for, in all normal cases, yes, it's fine, everything's definable. But I want to give the full idea and the full power of symmetric submodels. So I do want to work with the fourth order set theory just because.
So for example, in the construction that you're going to give of this failed model, is it enough to work in second order set theory?
Yeah.
Okay.
Everything's definable. It's all definable classes. So it's actually definable in, it's just GB. So it's all fine.
Okay, good.
But yeah, if I want to express a full generality of this theorem, I want fourth order. Because I like being annoying with fourth order objects. I don't know.
Another question. So when you think about these models, do you always basically put yourself in the situation of working in a universe of set theory, and this is a transitive set-sized model?
Yes. I mean, you should always, if you're doing 4C, it's always easier to work in a countable transitive model because, but it's sort of, it's best for conceptualizing it, but it's not really needed, in my opinion. So for the purposes of this talk, we're actually going to work in, let's say, V kappa plus 1, V kappa plus 2, V kappa plus 3, where kappa is inaccessible, just because that makes the world easier.
Okay.
But you need a lot less than that in order to actually define everything. But it's if you want to define it in full generality, you need to use some sort of higher machinery.
Right. Okay, thank you.
Perfect. Okay, so we've started with our model of fourth order set theory. Example being adding or many Cohen reals. We're now going to let G be our subclass of C2, be the group of order preserving automorphisms of P. So for example, the automorphisms generated by bijections of the orders. Now we're going to let K, which is our fourth order object, denote the collection of subgroups of G. And again, now because we've set it all up nicely, we could define F as a normal filter of subgroups in the way you'd expect. And again, the only reason I'm sort of working in fourth order set theory is so that means intersecting two hyper classes makes sense. And taking super hyper classes of hyper classes makes sense. And to say hyper classes as many times as possible. But the point is, if we work in a strong enough theory, we can define all of this. So we can define our filter normal subgroups in exactly the way we expect, and we can have our symmetric system in the way you would expect. And now for, let's say, a class name X, we can call it symmetric if those permutations such that pi of X equals X is in the filter. And again, HSF will be the hereditarily symmetric class names or whatever you want. Now, solely for simplicity, when looking at the symmetric model, we might as well only look at the second order part of it. Obviously, one can define a fourth order version of this without really making your life any more complicated. It's just notationally horrible. But yes, so we're going to have our second order part of it where we're going to have NG being those hereditarily symmetric sets and CG being those hereditarily symmetric classes. And as before, one can easily prove the symmetry level. So if P forces phi of X gamma, then pi P forces phi of X pi of gamma. And everything works nicely. So we've now done all the setup. So now I can give some examples of nice class symmetric models. So adding a Dedekind finite class, which is what I just gave the model for. So this is a class X such as no injection from omega into X, or adding our amorphous class. So this is a well-defined class system because it satisfies this whole principle that we've set up. Gittix model, so a model of ZF where every carbon has cardinality omega. Another such model is the Morris model, which appears as an exercise in YEC. And then Asaf Karagila wrote a very long article actually explaining how this proof works, because it turns out this exercise in YEC is very non-trivial. So this is a model of ZF plus for every alpha, there's a set A alpha, which is a countable union of countable sets. And the power set of A alpha can be partitioned into alpha many non-empty sets. And the other one is Monroe's model. So this is ZF with a Dedekind finite property class, which subjects onto V. So if I just skip ahead to this bump. So this answers Cameron's question of why I defined big in terms of surjections rather than injections. So it turns out that you can have a model of ZF K. So this is ZF with a one-place predicate K. And from any model M of this, there's a model N such that N is a model of ZFK, in which K is a proper class, which is Dedekind finite and can be mapped onto the universe. So by what I mean is this is a subjectively big class because it subjects onto every set, but it's not injectively big because omega does not inject into my class. Okay, so, but that was just to sort of say why I use surjections rather than injections. Okay, so these are examples. So now we can formalize our contradiction. So we have our model of fourth order set theory. We take our pre-tame class forcing, which is adding odd cross omega many Cohen reals. We take some generic, well, this is pre-tame forcing, so MG model set of symmetric power set. We take the class of automorphisms generated by a Reith product. Again, this is just the standard definition for an amorphous class. We let F be the filter generated by fixing finite subsets, and we take the symmetric system of this. So this is all well defined, and now you can sit down and you can write it all out, and NG will be the symmetric submodel. You can show NG contains an amorphous proper class. So the standard proof, which can be found in, I think, Drake's book on set theory, is a good example of this, is a model of N where there is an amorphous proper class. So therefore, by our earlier propositions, we have that collection fails. So this sort of tells us this is a symmetric submodel of a pre-tame class forcing, which doesn't satisfy ZF minus. And in fact, I have no idea what theory NG satisfies in this case. So just to give you an example of why I have no idea why something like replacement holds, I thought I'd give you sort of the general idea of, well, the actual replacement here. So again, let's take our NG that we built here. Let's suppose that P forces that F is a total function of A. What we want to do is, if we want to prove that replacement holds, we want to find a symmetric name for the range of F. Well, I'm going to start by saying, well, there is a name for F. So how one produces a name is you use collection, you find some collection of hereditarily symmetric names containing nice witnesses. And now this is the standard name, this B here is the standard name for the range of F in the full extension, where we use pre-tameness to find some nice sets and everything works out nicely. You want to then conclude that for either B dot or maybe a nice bit of an extension of B dot, that whenever we take any permutation which fixes both A and F, then it also fixes B. The issue is that for a general pair of names Y dot S, there is absolutely no reason why pi of Y dot S for pi being in the symmetries of A in set symmetries of F should be a set. So to just give you an example of all of this, well, these DXRs were determined using pre-tameness. These are just some nice small set with some nice properties. There are many choices for this small set which satisfies these nice properties. So in particular, instead of this S I've chosen here, I could have had in my B dot a name Y dot S prime, where S prime is this nice S that you picked here, union some useless information. And what do I mean by useless information in this sort of case? Well, the symmetries of A intersect the symmetries of F are things that fix some finite set. So therefore, there is a lot of things not in the symmetries of A intersect the symmetries of F. So what if I take some S prime here, which is S union with something which is not fixed by these? Now, when I take pi of these Y dot S's, the pi S's are going to be so many things. We're going to have a proper class of pi S's, or pi S primes, right? So therefore, we're going to have a proper class here generated. And there's basically no way that we can prevent this happening. So it seems as a general principle, without using some fancy technology somewhere, it doesn't seem possible that you can prevent the case that this thing will be a proper class. So what are we going to do about it? Well, what we're going to do is we're going to use a nice sort of definition, which was defined by Asaf Karagila when he wanted to do iterations of symmetric extensions. So we're going to call a name respected if, well, instead of looking at those permutations which fix X, we now want to look at those permutations such that one forces pi of X equals X. And we want these pi's to be in F. And as before, we let H, R, F denote the hereditarily respected names. We can then define the hereditarily respected model, and everything works nicely. So these are just those set names which are hereditarily respected, and those class names which are hereditarily respected. And now the point of why we do this is it will actually turn out that if P forces F is a total function of A, and we have this additional property that the set of pi's such that pi of P equals P is in the filter, then this B dot that we picked, so this just standard name for our total function, for the range of our total function, is hereditarily respected. So we don't even need to pick a new name. The standard name witnesses that replacement will hold. So everything's going to work nicely if we work with respected names.
Richard, sorry, I think I totally lost what was going wrong and how it's fixed. Do you mind going back to the previous slide?
So I will give you some more details about why this will all be fixed in a couple of slides. But essentially our issue was we have B dot, which is the name of the range of F. We now want to either take B dot or a small extension of B dot, let's say, which is then going to be closed under some permutations. Now, the only ones we really have access to are A and F, maybe some condition P if you really want. So these are sort of the only things that we can obviously think about to try and close B up. But the issue is that pi of B, so we want that the set of pi of B dots, but pi being a symmetry of A intersects a symmetry of F, we want that this should form a set. If this forms a set, then we've got a nice closure thing, and now everything works nicely, which is what happens in the set case. The issue is, in general, the collection of pi B dots for pi in the symmetries of A intersect the symmetries of F is going to be a proper class. So in general, you can't find a set-sized hereditarily symmetric name for the range. And therefore, you haven't proven that the range is a set in the hereditary symmetric submodel.
Okay, I think I see. Thanks.
Yeah, so, but it's going to turn out that obviously B dot and pi of B dot are the same because it's just a permutation that fixes F and A. But they're not actually the same. They're just forced by one to be the same thing. And this is why when we look at respect rather than symmetric, everything's going to work. Okay, so as I mentioned on this end of this remark, I needed that the collection of pi's such that pi of P equals P is in the filter. Again, this is a previously studied concept, and this is called tenacity. So we're going to say something is tenacious, a condition P is tenacious if there is some H in the filter such that for every pi in H, pi of P equals P. And our forcing is said to be tenacious if there's a dense subset of tenacious conditions. Obvious examples being adding an amorphous proper class, or adding a Dedekind finite set or a Dedekind finite proper class. These are all tenacious because our G was generated by things like fix E, where E was a finite subset of the ordinals. So just in the way we set up everything, because we have this really nice filter base, everything is automatically tenacious. And it turns out by Cargill and Hayut that every set symmetric system is equivalent to a tenacious one. So in set forcing, this is a perfectly fine thing to do. And in most class forcing, it's also fine. But this where I come to the first of my really annoying questions, which is that the proof relies on the completion of a corresponding Boolean algebra, which doesn't exist for class forcings in general. And in fact, what it involves is it would involve it to be closed under class joins, which is definitely not true for general class forcings. So I have no idea how to solve this, or if it should even be true, but is every class symmetric system, let's say P is pretame, equivalent to a tenacious one? Maybe it's true, maybe it's not. I have no idea. But anyway, if we now use tenacity, well, now I'm going to give you a series of lemmas which says everything works. So let's fix our model of fourth order set theory. Let PGF be our symmetric system such that P satisfies the forcing theorem. This is just to make sure everything behaves nicely. Let's take our generic and let's let NG be the respective model. The first thing is, if any generic MG is closed under Gödel operations, then the same is true for NG. And I should again point out, I don't know if this is true in the symmetric case. So this is true for our respective model. I can't prove it for the symmetric model because unions behave weirdly, essentially. The second one is that if P is pretame and our forcing is tenacious, then we satisfy GB minus. So this is with second order replacement, but not collection. So this gives us a nice answer then that the respective model does have a nice theory for pretame class forcings. And again, I should point out, in general, it won't satisfy collection because our model to add an amorphous proper class, you can then form the respective model, and as before, collection fails. But the important difference is we can actually prove replacement. So it's actually worth doing if you care about replacement. So then, just because this was a pretty picture, this is just why replacement holds in the model. And basically what I wanted to say is, well, we're going to take our name, as I said. So this is the name that we take in the class forcing case for the range of our function f. Now we're going to take some q, which satisfies some certain conditions. And now as long as pi is such that one forces pi of a equals a, one forces pi of f equals f, and pi of q equals q. So this is not one forces, this is actually true. Then q forces pi of b equals b. And because of the setup of b, this actually will mean one forces the statement. And sort of the reason why this all works and why we have the tenacity is, well, at some point we're going to take this condition T3 below Q, and we want that pi inverse of T3 remains below Q. Because it's below Q, we can then use predenseness to be able to find this S prime, which is compatible, and that's why everything works. And a similar argument works for separation. But the point is, we do need this tenacity assumption, otherwise I have no idea what happens to this condition pi inverse of T3, and the entire proof would break down. Okay, and now finally, we get that if P is tame, then the respective model satisfies full GB. And I should point out, this does not use tenacity. So tenacity was only needed for the pre-tame forcing. It's not needed for the tame one. And essentially this is because one forces, if we have tameness, one forces that B alpha is a set for every alpha. And pi of 1 equals 1 for every automorphism. And this is therefore a nice condition Q that we're working on. Is just 1. So everything works nicely. Okay, so now we've got the symmetric model, we've got that we know doesn't work in general, it seems horrible, and we've got the respected model, which we know has some nice properties. So now I want to sort of compare the two. And the first thing is going, well, if we take a pre-tame class forcing and we take some tenacious system, and let's suppose that if you give me a name X, then the collection of pi of X's for pi of G is a set. So this is saying that our issue that was caused, if I just go back here, so at the end of replacement, our issue caused here that the pi of our set, maybe a proper class, if we're going to assume this doesn't happen. So let's assume this doesn't happen. Then any hereditarily respected name, is forced to be equal to some hereditarily selected name by 1. And essentially this name is the union of the pi of X's for pi inverse of X. And now in this case, we get that collection holds. So in particular, our model satisfies, our model satisfies collection because of this fact that the pi X's can only be a set. And in fact, because of all of this, the respected name is the same as the symmetric name, which is then shows us that, in particular, when P is a set, the symmetric model and the respected model are the same. Yes, so just to sort of reiterate that, because that may not be clear. So if we have the hypothesis of this proposition, every respected name is forced by 1 to be equal to a symmetric name, which essentially means that the two models must be equal. So therefore, your respected the respected model and symmetric model are equal, and we have collection. So everything works really nicely, and this is actually what happened in Gittich's model. So this is a simple reason, basically, why Gittich's model satisfies GB without powerset, GB without powerset but with collection. But then you actually have to do all the difficult technical details to say why powerset also works. But yes, so everything works nicely. And then I should also point out that I think I have half an answer. I've not written it down because I've not convinced myself it's true. But I think in the case of both our Dedekind finite proper class and our amorphous proper class, they are actually equal to, the symmetric and respective models are equal, but it's highly non-trivial and a complete mess to try and write down. So this sort of leads on to my main questions, which I'm going to end with. The first being, is every class symmetric system equivalent to a tenacious one? So this is the question I had earlier. So the second question is, well, this sort of gave us a condition on the previous slide in which we can ensure collection holds. Can we actually have a nice combinatorial condition, which means it will hold and is equivalent to collection hold? And I've got partial work on this, which essentially says it has to be what I said on the previous slide. It seems to be almost the case that collection holds if and only if the respect and the symmetric model are essentially the same thing, because the pi of X is such that pi is in G form a set. If it isn't the case, it seems collection always fails, but I'm not completely convinced by it. The third question is then, well, what about powerset? I've given you a nice condition for collection. The actual interesting bit is, why does powerset hold? Essentially, can we give a nice combinatorial reason why, let's say, Gittich's model or the Morris model is a model of ZF? And now the fourth question, which is a horrible question, and I wish I knew the answer to, is are the respective model and the symmetric model actually different? So the whole point of defining this respective model was so that means we could actually prove things about the symmetric model, prove things about these symmetric extensions, but I can't actually prove it was worth doing because I can't show that these are actually different models. So yeah, that's what I'm currently working on. But I will end with just some references that I've talked about throughout this. And thank you very much for listening.
All right, Richard, thanks very much. Super, super interesting.
Yeah, thank you.
Any questions?
Yeah, I'm invisible, but it's not because I'm hiding something. It's because my computer camera is not working properly. So I apologize for that. But I have a couple of questions, actually. And if you don't mind, I'll start with a third. There are forcings which don't have automorphisms. Do you have to somehow, are they subsumed somehow in your machinery? That corner case.
If you have I mean, honestly, I don't know anything about forces without automorphism. I would assume then that essentially the symmetric submodels don't make sense. There are no symmetric submodels in that case. Well, the only ones are V and VG, so therefore everything is fine.
Yeah.
This involves, if there were no non-trivial automorphisms, then nothing interesting happens.
Yeah, I mean, to me, this is a sensitive topic because the first ones were constructed in my thesis.
Right.
Building a model of where V equals HOD and the continuum hypothesis fails. Next question, you deal with these symmetric models and whatnot. Now, in the old days, symmetric models, symmetries were used in connection with Frankel-Mastovsky models.
Yeah.
Is there any connection here? Could you get some proof of the axiom of choice failing and the Boolean prime ideal theorem holding using your kind of analysis?
In theory, it should be similar to adding a proper class of atoms. So if you take, if these ZFA models were with set many atoms, I believe it should be with a proper class of atoms. I haven't sat down and tried to write out any details, but that would be my guess.
Now, way back as the flood waters were receding, Dana Scott wrote a paper about what happens with ZF if you if you don't have the axiom of extensionality.
Yeah.
Is that kind of thing, is that relevant to the kind of analysis? Does it link up in any way with this analysis?
Not to my knowledge. I mean, I've looked at models without extensionality. I then run away very quickly because they're horrible.
Yes.
But yeah, so I don't know in particular, but I don't think they're particularly related to symmetric submodels.
Yeah. Now, the last question I have, if you guys bear with me, is when you say forcing, okay, what picture do you have in your head? Are you talking about something like Cohen's forcing with a formal language? Are you talking about Boolean valued models like in Yeck's book? Are you talking about Schoenfield's kind of realizability approach?
So, I mean, normally in my head, it would be some sort of countable transitive model, and you do the partial order, which is essentially the argument in CUNY, let's say. So I would say you would start with a countable transitive model, and then you can pick some element and you take your partial order like that, if that answers it. It's very much, I would do the nitty-gritty combinatorial forcing relation. Everything works that way, other than Boolean algebras in particular.
Well, thank you. It's been a pleasure. It's very pretty work.
Thanks.
Anyone
Could I
else?
ask another question, probably very naive question, but just trying to picture what's going on. So, like, if you imagine that your fourth order set theory model is just like the V kappa plus 4 or something like that of some bigger model. And you do, from the point of view of this bigger model, this proper class-sized forcing is just a set-sized forcing, and you could force over the big model now and construct the generic extension and form a symmetric submodel of the extension. And if you cut that down to V kappa plus 4 or something like that, is there some kind of relationship between these two constructions, like basically doing the construction just over the fourth order model versus
it should be basically the set forcing over V kappa plus 4 should be essentially the same as what the model for in the class model for.
And the construction of the symmetric submodel, if you do that over the, you think that would also
I think that would, that should all work out in the same, because I'm pretty sure that, I mean, I'd have to double check with people who know more class forcing, but essentially working over V kappa plus 1 and doing a set forcing over V kappa plus 1 and then looking inside that model is the same as a class forcing over V kappa.
So I wonder if what happens to these subtle distinctions between the respected model versus the other traditional symmetric submodel, because the differences don't seem to appear if you.
Well, the issue is what, it seems to be what the models can sort of tell, because it's a question of what classes are sort of definable over your model. So maybe that will cause issues, would be my guess.
Right. So you would have to be kind of careful about how you define, so to speak, the cutting down process to the symmetric submodel, right? Yeah.
I could imagine that'd be where, your issues would lie.
Interesting, yeah.
But yes, it's worth properly considering, because it's sort of one of these things that happen in the class forcing literature where you say, oh, it's basically the same as working in V kappa plus 1, but no one actually sits down and does it that way.
I think it would be like, it would maybe make it all more tangible, because everybody is used to working over models of ZFC. And if you could just embed it into the familiar process, somehow, just expending a little bit of more assumptions in the beginning, but, anyway, yeah.
It's those people who don't like just taking an inaccessible above whatever you're doing. So.
Right, yes.
I mean, Gunther, I think the issue is that V kappa plus 1 is a second order model, has a lot more strength, right? It's KM and more.
Sure. Yeah, totally. That's what I meant, like just expanding a little more extra assumptions. I mean, what I was really asking was not working over V kappa plus 1, but maybe letting lambda be the next inaccessible cardinal and working in V lambda and just so that you can work over a model of ZFC and everything is super familiar what you're doing, and then trying to understand what's the process, like how does it compare, forcing over this V lambda with P, which is from the perspective of V kappa as proper class, and doing the entire construction of symmetric submodel and so on and so forth. So you would have the symmetric submodel of the extension of V lambda and the one of V kappa, and how do they exactly relate and things like that. Yeah.
I mean, maybe a related thing. So the biointerpretability of V kappa plus 1 and H kappa plus, that gives you a biointerpretability of theories, KM plus whatever to this, ZFC minus without whatever. And I think it goes through also for this fourth order thing, the corresponding version. So V kappa plus 4 corresponds to H kappa 4 pluses. And so maybe something like that would give what you want. Because you're thinking of it then as you have like a larger structure and you cut off to like 4 steps above. And it should be an actual biointerpretability result.
Right. Yeah.
I mean, it's worth checking that, because there's part of me that feels like that should help, but there could be a size issue where I'm concerned.
So this actually leads to a question I had. So when you say fourth order ZFC, are you thinking like KM style impredicative comprehension for these higher order types, or is it all predicative or like GB?
So the ones that I've been able to write down are KM style and predictive style things, just because then it's easier to work out what your comprehension accents should be. The actual, what I think is an interesting question is finding a conservative extension of ZFC, let's say, which is fourth order. And that seems much harder to make.
I think there's stuff in arithmetic that's very similar. Maybe if you looked that up.
This is
put
what,
it
yeah.
over.
I know of.
I think there's
these
like
ones,
a
but I'm not-
version of like omega order arithmetic that's
Yeah.
conservative over ACA not.
Okay, I have to properly look at that. Because yeah, in a way, you sort of need very little machinery of GB, of let's say GB4, whatever you're going to call it, in order to define the symmetric submodel. Because you just basically need to be able to say, give me two hyperclasses, I can intersect them, I can
Right.
take supersets of them, everything.
I mean, everything you did looked definable, so it didn't seem like you would need
well,
paper
in
style stuff.
general, they will be, but if you want full, in general, when you take a class forcing, it's definable, so everything's nice. But in general, you do want to make it as any arbitrary class you take. And in particular, I think if we're going to show respective model is different from the symmetric model, I think that will have to be, that will probably involve a non-definable one. I think in order for this all to work nicely, yeah, if it's all definable, they're probably going to be the same.
Okay, sorry.
I have a question. Gunther, wait, I have a question. Sorry.
Good, good.
I was just waiting to give everybody a turn. So you mentioned that the proof that the respected model, I think if I remember it correctly, that the respected model is the same as the symmetric one, uses Boolean completions, which you don't have in class.
This is tenacity. So the proof that every set forcing is equivalent to a tenacious one.
Okay. So that would go through in sufficiently strong second order set theories, right? Where you have Boolean
So I'm not
Or-
sure it does, because the actual proof, so I tried to sit down and work this out.
Mhm.
The proof involves basically would involve closing under class length joins. And this is still not true in like ETR, in ETR.
No, I want way stronger in something in KM plus class choice, which is just by interpretable with the ZFC minus model, because you can do it there.
That does give you closure under class joins.
Yeah, it gives you everything,
Okay.
and then you should be able to have
Yeah.
that.
Then
Right?
then the same proof would go through in that case. Yeah.
Yeah. Okay. So then in those models, you would have equivalence, right?
Yes.
For the pre-Tayman tenacious. Okay.
Yeah.
Okay. So, I mean, it does seem to really, all of this hinges on the strength of your, I think if the counter example is going to happen, it's going to happen at at definable level.
Yeah, it's almost certainly going to be sort of a weird GB area where you can define.
So did you look at whether these two types of symmetric models are equivalent and strong enough second order set theories?
So I still can't see a way to do
KM
it.
plus more.
Yeah, I still can't see where you could do it. Maybe by going into the Boolean algebra, something like that. You could maybe
Yeah, that's
find
what I
a
would be.
tenacious one, and then you can take some nice closure properties. But currently, I can't see a way to do it.
Okay.
Just because you get the very simple issue of, if I just go back to, it's essentially the entire thing's going to break down, because you have to somehow be able to choose a name for your range or whatever it is. You have to be able to choose this really nice name, which is somehow closed under permutations. And I can't see any way that you can somehow construct this name, so you can't decide what your S's you want to have are. It just doesn't seem possible.
I see. I see. Okay. Can you send me your slides?
Sure.
Yeah, I have to admit, I don't quite understand the details of this particular problem, but it sounds somehow naively kind of like a Scott's trick type problem. Could that be like if you
could take the ones of minimal rank, the
Right.
issue is what happens if your permutations don't respect rank. So the example here is if we're adding odd many Cohen rules, you've sort of got
Mhm.
odd many things all of the same rank, so you
I
can't do a
see.
Scott strict stuff.
I see. Okay. Mhm.
But this is what happens in things like Monroe's model with the Dedekind finite set. It does all work because everything is going to have small signs, so you can take the permutation bounded by some rank.
Okay.
Even for example, the simple one being adding a Dedekind finite proper class. So your permutations are just automorphism of the ordinals, and you fix finite sets. Even if I do something like that, then it just seems like there's no way to construct these things. And the only reason why I think they are actually going to, the spectrum model and symmetric model, I think will still be the same in this case, but that's for completely different reasons, which I've been trying to write down, and it's horrible.
Okay. All right, is our curiosity satisfied? Okay. All right, great. Well, thanks a lot for this talk. It was very interesting.
Thanks, Sharon.
Thanks, Richard. Really interesting. I want to think about it more slowly, so I want your slides.
Sure. Yeah, it's sort of one of those things someone should have looked at and should have all the answers to this, but it seems not to have been thought about properly yet.
Yeah,
It's nice to find things like that. So.
Yeah, and it turns out it hasn't been thought about because it's really complicated.
I'd welcome a copy of your slides as well.
Yep.
Okay. All right. Have a nice weekend, everybody.
Have a good weekend, everyone. Bye.
Okay, bye, everybody. Bye.
Bye-bye.
Right.